So these are the basics you need to know about current and resistance when you're dealing with any kind of circuit. All right, so current, first of all, we use the symbol I. In magnitude, it is the rate of change in charge over time. It does have a direction, so I is a vector. We can use this to find the magnitude, and the direction is going to be, it goes from, so it flows from high voltage or high potential to low voltage or low potential. So usually, if we've got current, we think of it in maybe a wire, which is a cylinder, like this. And if we just kind of like slice the wire, we will get a cross section. So we can have an area in here that is just the cross-sectional area of the wire. If this is high voltage on this side and this is low voltage on this side, and then the current is going to flow down the wire like that. Let's see, one other thing I should tell you is the units of current are amperes. And as you can tell from this equation, amperes have got to be equal to coulombs over seconds. So amperes equal coulombs, the unit of charge, over seconds, the unit of time. All right. Now, sometimes we want to look not at the total current flowing through the wire, but rather what the current is doing in the different parts of the wire. So to do that, we will actually look at the current density. And for that, we use a big capital J. And the units of this guy are coulombs per second, so the unit of current, divided by meters squared. And that's because current density, like any other density, is the thing you're interested in divided by some kind of geometric thing. So in this case, it's area. So this is a area current density. And so in order to get back to the total current flowing through the wire, we do pretty much the same thing we always do with any densities. We are going to take the current and, oops, forgot that one's not going to be a vector, and we are going to dot it with a little bit of an area element and do a surface integral. So basically what we're doing here is we're looking at how much current flows through that area. And remember, area always has a direction we can attach to it that'll be perpendicular to the surface itself. And so this dot product matters. We're only interested in current that's flowing through the surface, not across the surface. But we do that dot product and we integrate it over this whole area, and that gives us the total current flowing through this wire. And the direction of J is going to be the same as the direction of I, of course, because they will flow in the same way. Just one of them you're looking at the current at each little chunk of wire, and one of them you're looking at the current throughout the whole wire. And a lot of times you might have like more current, for example, or more charge moving on these outer edges of the wire rather than in the middle or something like that. And so that's why current density is useful. All right, next, resistance. And for that, we use the symbol R. And what we're really doing here is it's resistance of a circuit element. And by that, I just mean anything you might stick in a circuit. So like a resistor would be a circuit element, a wire would be a circuit element, anything that you can stick in there. It has units of ohms. So, which we use a big omega, and this will usually come up in Ohm's law. And Ohm's law is simply the current through a circuit element will equal the voltage across it divided by the resistance of that element. And Ohm's law is what we call a empirical law. It means that we didn't derive it from the fundamental beliefs we have about how the universe works. Rather, it just is a really good model a lot of the time for what's going on in a circuit. So for many circuit elements, the current through them is going to get bigger linearly with the voltage across it, and it's going to be mediated by the resistance of whatever that element is. So larger resistance will be less current flow, because again, the resistance is the resistance of the circuit element, oops, didn't finish that sentence, to current flow. The more resistance you have, the less current flow you've got. All right, so those are the basics. In the next video, I'm going to dive into the details of what's actually going on to the individual bits of charge and things.